Hello and welcome to Han Academy. Today I'm going to be going over a very realistic and very likely, in fact, scenario where you might have to apply mathematics to solve a problem. Um, and yeah, so this will probably most likely happen to you. So it's a good thing um, to know how to solve this problem. So imagine you're at a fried chicken place, or even, like a yogurt place or an ice cream place, really anywhere with cylindrical bowls. Um, and they have two options for the same price, right? So they have one that has a radius of 12 inches and is 16 inches tall, and another one which is a radius of 20 inches but is only 10 inches tall. So you can see the dilemma here, where one is taller but skinnier, and the other one is wider but shorter. So you want to know, well, how can I calculate the volumes of these two different bowls in a efficient and practical way while I'm standing in line, so I can get the most bang for my buck and get more volume per dollar I spend? Well, there happens to be a mathematical way to calculate these volumes, and it really is just um, what is it saying? A hop, skip, and a jump to the solution, and that is a triple iterated integral using multivariable calculus. So let's do that. So first things first, let us we already have sort of a visual representation of the bowl, but let's just do another one. So it's going to have a radius of 12 inches. So it's going to look something like this. Excuse my representation. Oh, sorry, you can't even see it. So it's going to look something like this. This is a 12. There we go. That made it more clear. And it is 16 inches tall. And we're just going to center it at the origin for the sake of simplicity. So now, in order to evaluate this, we're going to need to set up or define the bounds of which we are integrating, right? So we could do it, let's see here. We could do rectangular coordinates using dx, dy, and dz, but that would involve using like square roots and defining circular, arcs and stuff. And let's be real, while you're standing in line, the line's moving kind of fast, and you're kind of thinking like, oh God, I don't know what to order. So you really don't want to be doing super complicated, radicals and stuff like that. Um, so there has to be, let's just use another coordinate system. So we can use the cylindrical coordinate system. And hey, we already have R defined here. So that's already one. That's pretty much done, right? So R is going to be between 0 and 12. Now in cylindrical coordinates, it's R, theta, and Z. So theta will be from 0 all the way around the full circle. So it'll be 0 to 2 pi. We're doing it in radians. And Z will just be from the bottom of the bucket, which is at Z equals 0, to the top of the bucket, which is at Z equals 16. So these are our bounds, and now we can set up an integral using these bounds. So let's just write these bounds out. I'm going to do theta last. Let's just do Z second and then R first. So it'll be dr, dz, d theta. Now remember, when you use cylindrical coordinates, you're going to want to multiply in and r, right? So this is going to equal the volume. Let's just make sure it's clear what we're solving for. And, let's just keep in mind, sorry, what was I saying? Right, integrating. So let's integrate this. So it's going to become this. And you'll have to excuse me, I'm doing this on a mouse, or with a mouse. So there's a lot of clicking involved. So evaluate this from here. Now, if you don't know how to do a triple or maybe even a double iterated integral, it really is just like doing singular integral, except you're doing it double or triple. I'm sure that makes it very clear. So now we have 0 to 2 pi of 144 over 2 z evaluated from 0 to 12 or 16, sorry, d theta. Let's just come over here because things are getting a little bit smushed. So we have 144 over 2 times 16 minus 144 over 2 times 0, but we're not going to write that because we're all about saving time, which is why we're doing it the most efficient way. D theta, 0, and 2 pi. And then lastly, we just do 144 over 2 times 16 times theta evaluated from 0 to 2 pi. So now we're going to have a beautiful answer of 144 over 2 times 16 times 2 pi. Minus obviously this times 0, but we're not going to write that. And when you evaluate this out, it becomes 144 over 2 times 16 times 2, 2304 pi. Now let me just make sure I got that right. Yeah, that is right. So this is the volume. Oh, sorry, we should specify cubic inches. This is the volume of the first bucket. So let's just write that over here. 2304 cubic inches. And now we just do the same thing with the second bucket. And let's just do that really quick. So we're really just going to be doing the same exact thing here. R will be between 0 and 20 this time. Theta, once again, will just be the entire circle, 0 to 2 pi. And z will be a little bit shorter this time. It will be 0 to 10. So again, let's set up this integral. Let's do 0 to 2 pi again. Then let's do 0 to 10. Then let's do 0 to 20. R, dr, dz, d theta. This will equal the volume. So I'm just going to sort of do this a little bit quickly here. Just come over here. So it will be 200 z evaluated from 0 to 10. This integrated from 0 to 2 pi. D theta, that'll be 2, 1, 2, 3. D theta, 0 to 2 pi, which will be 2, 0, 0, 0. Theta, wow, that's a funny looking thing. pi, which is 4, 1, 2, 3 pi. And that is your answer. So the volume of the second bucket here, right, is 4,000 pi cubic inches. Wow, that is way bigger than the other one. So now that you've done all that calculation, probably in your head, or maybe, on a napkin or something, you will know definitively that bucket 2, although being the same price as bucket 1, is almost double the volume. And yeah, so I hope this helped, and I hope that next time you're standing in line, or maybe you're shopping online or something, and you see two similarly priced buckets with differing dimensions, I hope you can think of this video and think to use a triple iterated integral to calculate the volumes and then compare the price per volume or volume per price and pick the better deal. So yeah, hope this helps and have a spectacular day.